Hello, everybody. Thanks for joining our new webinar about the high voltage circuit breaker testing. My name is Simone Meneghin. I am Regional Sales Manager at Altanova, a double company. Altanova, a double engineering company, provides diagnostic solutions to utilities and industries to improve the performance of their electrical assets, to portable testing equipment, advanced monitoring systems, and professional services. A brief history of Altanova: in 1938, ISA, Strumentazione Sistemi Automatici, is established in Taino, in the north of Italy. In 1999, Techin was born as a spin-off of the University of Bologna, here in Italy. And in 2017, ISA and Techin merged together, giving birth to the Altanova Group. 2 years later, in 2019, Intelliso joins ISA. Altanova. Intelliso is an American company, specialist for medium voltage asset monitoring. And in 2021, Altanova Group became part of ESCO Technology Group and joined the double engineering company as part of the USG division. 100 years of activities. All the company of the groups could design and sell on the market a wide range of different portable equipment and monitoring systems. Now the Altanova Group is present in more than 100 countries. We have 12 global facilities location and 150 employees and several customers all around the world. We have a solution for every asset. One of these is circuit breaker. That is the subject that we are going to discuss today. The circuit breaker is an automatically operated electrical device, and it is designed to close and open contacts inside chambers. This operation must be done in the fastest possible time, because we have to clear the fault in the shortest time as possible. If we look inside the circuit breaker, we have to imagine that the current is flowing into metallic parts that touch each other. In the way we say that the circuit breaker is closed. But when the open command is issued, then the two metallic parts start to be separated, and when this operation starts, there is an arc that is flowing from one part to another, and this condition must last for the minimum possible time. When the two metallic parts are well separated, then the arc is not present anymore, so the current flow is interrupted. The reason why the arc must remain for the shortest possible time is because this arc can damage the surface of the metallic parts. And this arc must remain no more than a few tenths of milliseconds. Otherwise, as you can see in the picture, this is the effect that you get. The main contact is designed to withstand hundreds of normal load current interruptions, but in case of fault, the current is extremely high, over 1000 amp, and when the circuit breaker interrupts such a high current, the remaining life of the circuit breaker is significantly reduced. So let's say the number of operations under fault conditions is no more than a few tenths. According to the rated voltage of circuit breaker, you may find more than one break per phase. For example, if the voltage is higher than 230 kilovolt, usually you find 2 breaks per phase. In older design of circuit breakers, you can find more than 2, maybe 4 breaks per phase. In case of medium voltage switch gears, the concept remain the same. In medium voltage switch gear, you will find only one break per phase, and the dimension is much less. These devices are designed to operate at lower voltage. That's why the size is much less. But again, the testing principle is the same as a high voltage circuit breaker. Coil commands are, as the name suggests, the device that trigger the operation. So the coil command will trigger the springs. The springs contains all the energy that will be released to the mechanisms that go to open and close the main contact through mechanisms, through mechanical leverages. The status of the circuit breaker is monitored through auxiliary contact. For example, protection relays and SCADA systems knows about the main contact position through this kind of auxiliary contact. So these are parts of the breaker that needs to be tested, because if there is a problem on auxiliary contacts, then all the devices in the substation will not get the right information and cannot take the right decision. There is also a motor that charges the springs, and what usually tested is the current of the motor and the power absorption of the motor. This is a typical example of results that you can take out of a measuring system device. This traces belongs to the main contact. So the thick line represents the close position, and the thin line represents the open position. With two different colors, we are indicating the traces that belongs to main contacts and to the auxiliary contacts. We can see that the auxiliary contacts are gas the information of the open and closed position. Here you see the profile of the coil currents during the operation. It starts from 0, it reaches a maximum, and then returns down to 0. The operation time is measured from the moment that the coil is energized. So from the moment where the current starts to be higher than 0. What parameters should be kept under control? We have to control the status of the coil commands, the parameters that represents the status of these coil commands is the peak of the energizing current. If it is too high or if it is too low, represents an issue. The flow time of the energizing current. If there is a problem, maybe this time is taking too long. And the shape of the energizing current also give some information about, for example, the mechanisms. We will see in one slide more in detail this concept. For the main breaker contact, of course, we have to test the opening and closing time, but not less important, the value of the resistance when the circuit breaker is closed, and also the profile of the dynamic resistance during the operation. Understand the status of the arching contact. For the auxiliary contact, we have to check if they are working correctly by measuring the switching time, and when it's present, we have to measure the pre-insertion resistor value. The pre-insertion resistors are devices present to absorb energy when during the operation. It's possible to add some transducers in order to test the movement of the main leverages and also the speed of the movement. circuit breakers must operate in the fastest possible time. And for motor, we can use, for example, current clamps in order to check the operating current of the motor. If you want to do a test, it's possible to, for example, use a CBA 3000. It is a device designed exactly for these purposes. It is provided with several digital input for the time measurement of main and auxiliary contacts, and it is also provided with coil commands up to 6. In case of high voltage circuit breaker, you may have 3 independent command for the open and 3 independent command for the closing. We have up to 8 analog input for test. For example, you want to measure the voltage from a current clamp, where you can measure the voltage during a resistance measurement. The voltage is a voltage drop that is generated by the current that is flowing into the contact, and the current can be generated. So CBA 3000 can generate in the same time 3 independent currents up to 200 amps. The normal way to understand if the main contact is open or closed is to measure a resistance value. When the circuit breaker is closed, the value of the resistance is extremely low. And when it is open, this resistance tends to go to infinity. So if we are able to detect the moment where this value change, so from a very low value to a very high value, we are able to understand when the circuit breaker is closed and when the circuit breaker is open. But when we use an electronic device, we have to put a threshold somewhere in order to understand what does it mean low value and high value of resistance. In this representation, you see dashed line that represents exactly this threshold. Typically, this threshold with, let's say, standard devices is around 10 ohm. It's a reasonable value because when the circuit breaker is closed, the value is in the range of a few micro ohms. So it is a short circuit. So whatever is higher than 10 ohm is clearly something correlated to an open position. What do I need if I want to perform this test? For example, I can connect the main contact to a timing input of any standard circuit breaker analyzer, and as well I have to connect the coil command because I need to control the moment where the command is issued, because in that moment I have to start the timer. So I give the command, I start the timer, and I check when this resistance change status through this dedicated input. One break per phase, we connect just one input like this. If I have 2 breaks per phase, I have a common point in the middle here, and the first break and the second break. This connection must be repeated for all the 3 phases. In this representation, we have only one for simplicity. The high voltage circuit breaker is a big device. So if you need to connect the clamps on top, typically you need a ladder or an elevator. The wires are connected to the timing input, and we can see here that on CBA 3000 there are LEDs that indicates the status. Green, the green LED indicates open contact. In case the contact is closed, this LED becomes red. So you have an immediate feedback about the status of the brakes. This is quite useful because not always is possible to understand if it is open or closed, simply because you don't have any other possibility. Let's see a few simple examples for the close and open operation. As I said before, the timer needs to start when the coil is energized. So both situation, the timer starts from here, and we can see that sometimes the main contacts are not well synchronized. And this is also a measurement that is important to be done, because if one of the contacts is too slow, it will create a problem in the network and in the circuit breaker as well. Important that you use a method to measure with high accuracy the switching time, the tripping time of the main contacts. Inside the springs of the circuit breaker should be enough energy to guarantee a reclosing cycle, because in case of fault, at least one tentative to reclose the circuit breaker must be done. For example, if the fault is a lighten, once the lighten touch one of the tower, immediately after it disappears. So default to at least try to close the circuit breaker and put in service once again the line. So in this situation, the circuit breaker must open and close after, let's say, 500 milliseconds, and all the energy must be stored inside. There is no time to wait that the motor charge again the springs. But there is also the opposite situation. The fault will not disappear, but remains. In this case, the circuit breaker, after it tried to close, for sure, there will be again the fault current that is flowing, and then a second open command must be issued. For this reason, on the nameplate of the circuit breaker, you will find an indication like this: operating sequence. O means open command. T is a waiting time, or to be more precise, is called a dead time between the open and the first close operation. This time can be quite fast, less than 1 second, let's say 0.3, 0.5 seconds. In this case, we are talking about a fast recloser, but it can also be long, higher than 30 seconds, can be a minute. In this case, we are talking about slow reclosure. This close command and open command without a time is representing the switch on to fault logic. So this means that there is no intentional time delay between operations. Must be underlined that this sequence is the most critical, because you can imagine how much energy must be stored inside the spring in order to guarantee that this operation will happen with the time that you expect. This is an example of what you can get if you try to test a reclosing cycle. This is command, and we see that all the phase, in this case, we have a 2 breaks per phase circuit breaker, 6 breaks here. So we have open command, all the breaks change status from close to open. After 300 milliseconds, there is a close command. Then the start to close, and only when the main contact reach the close position, then the second open command will be released, and again. It's important to test the time delay between the second close command and the second open command and the close command, because this delay should not be too much. This is also another important time that we have to test, because this is called dwell time or short circuit time. You can see that when you try to reclose on a fault, in this time, the current will flow in the main contact. So this must be less as possible. This is the proof. This is a real results that the circuit breaker can perform a complete close-open sequence in a very short time. In this example, is 78 milliseconds. With CBA 3000, it's possible to choose this sequence in a very easy way. There is a button, is a selection button that will give you the possibility to choose if you want to do just a close operation, an open operation, or a combination of the two, close open, open close, or the open close open. The results will be in the end displayed into the color screen here for the interpretation of the results. Now we will see the concept of the static contact resistance. Important that the value of the resistance remains well below few of microamps. I try to explain with numbers. If we have a load current of 100 amp, this is, let's say, a reasonable value for a load current that flows into 100 micro ohm as a contact resistance. We see that the power dissipated is 1 watt. But if something happened to contact, and the resistance value will increase, we see that, for example, if the value goes up to 100 milliamp and the load current remains the same, the dissipated power is in the range of 1000 watt. And have in our houses oven and hair dryers that can dissipate more than 1000 watt, and we know how much heat it can produce. So this condition cannot remain for a long time. You have to remember that the heat is a function of the dissipated energy power. So it is very depending on how much time this situation is long. So I can have a very high power, but if it is dissipated for a very short time, it will not be a big issue. Vice versa, if you keep this condition for a long time, it will be an issue. But how to test in a reliable way a very small value of resistance? The first idea can be, I take a multimeter and I measure the resistance, because we trust a lot in our very good multimeter. but there is a problem. You can take the best multimeter with infinite precision, but it will not give you the right value because it uses the so-called two wires method. It has a problem that you cannot avoid, and it is this one. In order to measure the resistance, you have to inject current and measure voltage. And the current source is inside the multimeter here. It is better represented in this scheme. So the current that is generated flows into the wires, and these wires goes to the contact. So I cannot avoid to measure the contact resistance and also the resistance of the two wires. It's very unlikely that the resistance of the two wires is much less than a few microns. So this is not possible. This is not a possible test that you can do. You can keep the multimeter, but you can use it as a voltmeter, and you need an external source of current. In this way, you are implementing the so-called four-wire method that avoid the issue as explained before, because the current generator inject the current into the contact resistance, of course, through wires. These wires have its own resistance, but this doesn't matter because we are measuring the voltage with another device, and in the wire of the voltmeter there is no current flow because every good voltmeter has a very high input impedance that prevents the flow of current into this wire. So it is not possible to have current. Okay, nothing is zero, so there will be a very small amount, but it will be so small that you can neglect the error introduced by this. Again, measure the resistance by measuring the current and the voltage, and then you apply the Ohm's law and you get the value that you're looking for. The four-wire method is mandatory, but is not enough to guarantee the most correct value. Some precautions must be taken. First is you have to pay attention where you place the clamps, the terminal for the voltage measurement. If you make a mistake, then you get wrong values. Test current must have a high amplitude, because if you want to measure microohms, then you have to inject a very high current in order to be able to measure millivolts at least. If you generate a very small amount of current and then you have to measure voltages in the range of microvolts, for sure it will not be accurate. The current generator that you choose must be very stable. You current without ripples. And when you are in substation, you have noise, and then you need a device or a method that is guaranteeing a very good noise rejection. Now we explore why the position of the clamps is very important. Let's imagine to use a copper wire, and we want to measure the resistance of the copper bar. The resistance of this copper bar is defined in this way. You have a number that represents the copper resistivity. Longer is the bar, higher is the resistance. Wider is the section, lower is the resistance. If we input some reasonable numbers in this formula, we can get a reasonable value of resistance. In this example, we have, let's say, 28 micro ohm. I can imagine that this copper bar is a series of smaller copper bars are connected in series, and the sum is again 28 micro ohm. I can divide the copper bar in an infinite number of elements, but let's keep 4 for simplicity. If I measure the voltage in this position, for sure I am measuring the 4 elements and I get the right value, 28 microohms. But if I change the position, it is, as in the picture, it is equivalent to measure only 2 of the 4 elements. Then I get 14 microohms. If I look the error in percentage, I'm making an error of 100%. You can see with this very simple example, the demonstration, how important is the position that you choose for the clamp, for the voltage measurement. Here you can see, this is the clamp for the current injection. This is just one of the 2 sides of the main contact. So you may think that if you place anywhere the clamp of the voltage, you will get correct results, but this is not true. This is the value that you get with the clamp in this position, and this is the value that you get with the clamp in this position. This is correct, this is very wrong. So a good practice is that maybe you can take a picture of the first measurement, and the second time you try to repeat the same measurement. By looking at the picture, you will place the clamps in exactly the same position. So the value that you are getting are comparable. In case of medium voltage circuit breaker, the concept is the same, but maybe you can find a situation like this. So it's difficult to place the clamp always in the same position. It is suggested to have adapters to be in order to guarantee the best repeatability of the measurement. The test current must have a high amplitude value. As I said before, if I generate a very low value, let's say 10 amp, I have to measure voltages in the range of microvolts. So it is recommended to test the static resistance with at least 100 amp. So the voltage can reach the 2.8 millivolt. But even if you want or you cannot to generate such high current, but you trust a lot in your multimeter that can measure the voltage with extremely high accuracy, you have to remember that there is one aspect, the so-called Seebeck effect. In the moment that you are connecting together 2 different metals, the junction of these 2 metals will produce a very small voltage in the range of few microvolts. For example, this is the principle that makes a thermocouple working. So you have to take in consideration that small voltage is created only because you are touching the copper with your clamp, and you have to compensate this value. And believe me, it's very difficult to estimate what is the value to be compensated. So it is highly recommended to find a good high current DC generator. But if the high current DC generator will introduce ripples, then it will be difficult for you to have a accurate results. It's possible to apply some mathematical compensations in order to extract the DC component of this not DC signal. But there is another aspect to take in consideration. If you have a ripple, maybe this peak is much higher than this minimum. So in order to measure the complete waveform, you have to choose a range in your multimeter that is not suitable to measure low voltages. So you are introducing two different inaccuracies. The first is the mathematical approximation. Second is the range of the voltage that is not good for low voltages. So the accuracy is not the best. It's again, pure DC signals guarantee the best accuracy. Substation, the electrical noise is for sure present and can be very high. The solutions that you can find is the use of shielded cables and introduce sort of filter. So you have to filter all your signals that you get and try to remove the line frequency. It can be a 50 or 60 Hz superimposed to the value that you want to measure. With CBA 3000, you can make all these operations with very high accuracy. So the device is doing for you all the job. It applies noise rejection with algorithm, numerical filters, and also the cables are shielded, and you can do the test up to 6 resistors simultaneously because it's provided with 3 current generators and 8, but in this case you can use 6 analog input to perform this measurement. The dynamic contact resistance is as well a very important parameter to test. When the circuit breaker is opening, the arcing contact is absorbing energy that is generated by the arc. Arcing contact must be in good health. So what you need to check the status of the arcing contact is to, for example, start the current generation. When I mean current, I mean the DC current generation. Then you issue the open command. You keep the current until the main contact is fully open, and you have to record the current variation with at least 10 kilohertz. That means a time resolution of 100 microseconds, because the operation is very fast. We have to remember that all this happens in a few milliseconds, so you cannot measure all the signals with the low sample frequencies. And the setup in terms of wirings for this measurement is exactly the same of the static resistance. So all the considerations that we discussed for the static contact resistance applies for the dynamic resistance. This is a real measurement. So we start from the moment the circuit breaker is closed. So the main contact, this is the main contact, and this is the arcing contact. So the circuit breaker is closed, and the in the graph the value is very, very low. This moment the main contact is open, but the arcing contact is still closed. So we start to see an increase of the resistance value that will stay for a few milliseconds, and then the main contact, so the circuit breaker, is totally open. So the value of the resistance in the graph goes to a high value. So each time the circuit breaker interrupts the fault current, part of the arcing contact surface burns, and the equivalent length is reduced. So we can convert the length in time, assuming that the speed is constant and constant during the operation and constant between operations. Shorter is the time, shorter is the arcing contact. So if I overlap two graphs and I see, for example, a deviation like this, this is clearly a problem in the arcing contact. And the minimum acceptable length is defined by the circuit breaker manufacturers. All the examples that we have seen in the previous slides belongs to the open operation. But when you try to do the same measurement when you close the circuit breaker, most probably you will not find a good graph as you can find during the open operation. The speed of the contact, first of all, is higher, because let me go back to the previous slide. We start from the close position here, then here is where the contact starts moving. So we assume that the speed in this part of the operation is much less than in the end of the operation. The speed will not help to have clear graphs, and also you are applying a higher current change, because you are from a situation where the current flow is, let's say, 0, then the contacts start to close, and then you go from 0 to the maximum, and this for sure introduce some noise in your measurement. So if you want to check the status of the main of the arcing contact, it's better to do the test during an open operation. Okay, this is a real measurement performed with another equipment. In this case is CDA 1000. This is a graph of a dynamic resistance during a close command. So the graph starts from a very high value, goes down, then there increase, so there is a second peak in the measurement, and this is clearly something that indicates problem in the circuit breaker. The same information is confirmed by a standard time test. It's clear here that there is a bounce. So this, let's say, hole correlated to this peak here. So the two measurements are confirming the problem somewhere in the phase B. Most probably is a problem in the mechanisms. For example, the main contact close, but there is a problem in the mechanism, so there is a bounce, and it's not touching very well here, and then it returns close position. So it is important combine the two measurements, because sometimes the two measurements confirm that this is a real problem. So you can avoid doubts. Maybe you can doubt that this is a good measurement. Maybe you can doubt this is a good measurement, but if two different measurements with two totally different approach give the same information, you can safely say that the measurement is reliable. There is the possibility to introduce in your measurement setup travel transducers or motion transducers. The purpose is to acquire the actual movement of the mechanism during the open and close operations. There are, let's say, two main family of transducers, rotary and linear. The choice between the two is very depending on the mechanical layout and design of the circuit breaker you need to test. The most simple transducer basically is a variable resistor. So it is necessary to apply a voltage to the transducer, and there is a slider that is changing the position of the arrow in the scheme. So we are going to measure the resistance between this point and this point. If this change, then of course the value of the resistance change. If we acquire the voltage during the movement, during the operation, then we are getting information about how this movement is performed. It is necessary to correlate the delta of the voltage with the delta in millimeters, because in the end we wanted to make a motion analysis. So we need something that converts the voltage that you get out from the transducer into millimeters. CPA 3000 is possible to input few parameters, and all this calculation is performed automatically. All these numbers are necessary when you want to use analog transducers, because for sure you need to define what is the supply voltage, what is the total stroke of the transducer, and what is the actual stroke of the circuit breaker. In case you are using rotary transducers, but it is analog transducer, the principle is basically the same. It is even more easy to perform this kind of analysis if you are using digital transducers, because in that case you don't have to input parameters, just a couple of parameters, and the measurement will be performed. For example, in case of digital transducer, you don't need, for example, to define this kind of stroke. Don't need to pay attention on the position of this, because the transducer, you are going to measure a train of pulses, and then all these concepts are not applied. The speed is measured by defining 2 points and just applying this simple formula, the space divided by time, and you get the speed. These 2 points can be defined in different ways. The 2 points can be independent one of each other, so the operator decide where to put these 2 points, but this is not the most used approach. The most used is to set the point A when the main contact change status, and the point B with an offset. Can be an offset in time, or can be an offset in distance. In this way, you are sure to get the measurement in a reliable way, because at least the point A is defined automatically, and the point B as well, because you are just defining an offset. You don't have to remember the absolute position of the two. And when you decide the absolute position, you have to pay attention, because you have to place the 2 points where the slope, let's say, is constant. You cannot place 1 point here, 1 point here. Otherwise, the speed will be affected. The real results. This is the graph that you get out of a transducer, and this is a graph for the dynamic contact resistance. The combination of these two graphs can give you the length of the arcing contact in millimeters. For example, in this case, you can see this is where the main contact is open, and what is remain closed is only the arcing contact. By measuring these 2 points, you are getting the measurement in millimeters. Not always is possible to make such good analysis, because the use of transducers needs much more time, because you have to place the transducer, you have to spend some time in doing it properly. But if you can add treble transducers and perform the measurement of the dynamic resistance in the same time, then you get the best test, the best information. Once you have this graph from the transducer, then you can do some automatic calculation. For example, as we said many times, the total stroke, the speed, the over travel, where the over travel is I reach the final position, but I will go over. Then there are some oscillation. That's why we have a measurement called rebound. And then we get to the steady position. So all these information are important and must be measured and kept under control. All these measurements are performed automatically by CDA 3000. There are some mounting example. So this is one possible situation you can find, but of course in the field there are so many different circuit breakers that I'm sure that if you check in your circuit breaker, the situation will be much different than the one in this example. So this is a shaft that is touching this moving part, and then we need to introduce between the rotary transducer and this shaft a damper. This guarantee the best accuracy of the measurement, but in the same time it save the transducer itself, because the damper is also absorbing some shocks. The position of the transducer is very important. It must be done with high accuracy. If you make a mistake in the coupling, in the mounting, then your measurement will not be good. This is another example where it's possible to use flexible shaft with magnets or with screws. So the concept is that for every circuit breaker must be checked what is the mechanical layout, and according to that you need to find the best mechanical solution to connect the transducer. You cannot do this job without the proper information. You need to make a survey and understand. We are available, for example, to have a discussion with you. If you have questions, you can let us know with pictures what is the best way to perform the test, and we can provide our suggestions. We don't have to forget that the circuit breakers are in substations and very close maybe to live bus bars. It is important to perform all the tests in safe conditions. When the circuit breaker is out of service, for sure, the two sides of the circuit breaker are connected to the ground. Because whatever is floating, substation can easily reach very, very high voltage, dangerous for the operators. So this is the condition that you would like not to change. But if you are using the standard method, one of the two ground must be removed, because if you remember in the beginning of the presentation, the way to perform the measurement is to check if the resistance is going from a very low value to infinity. But if you have the two sides grounded, this is not true. You are going from a low value of resistance to another value that is not for sure infinite, and maybe extremely low. So this delta can be low. So I need a device able to detect this small delta. And for sure, the standard method don't guarantee accuracy in such a condition. The reason why you have this small delta is because when the circuit breaker is open, what you measure is the resistance of the ground leads. They are good conductors, so you have to expect a very low value for this resistance. So traditional method will not guarantee that you are able to understand when the circuit breaker is open, so you need an advanced method. The method that we suggest is to inject a high current, and why not using the same generator that you are using to measure the static and dynamic contact resistance. Then you open the circuit breaker, then for sure the current drops because the total value of the resistance is increasing, and in the same time the voltage is increasing because the total value of so this is what you get. Here is when you open the breaker, and here close the breaker. So if I make an analysis from this signal, I am able to understand when the circuit breaker is opening and when the circuit breaker is closing. But this is an ideal situation. This is a simulation. So it's very easy to perform the measurement if you are in laboratory. But when you are in the field, the situation is extremely different. First of all, you have a 50 Hertz or 60 Hertz signal that is in cables. For example, if you take wires to inject current and the circuit breaker is closed, then you are creating a coil, and all the electromagnetic field that pass through this coil will induce current in the cables, and this must be removed. The same happens for the voltage, of course. The solution is to apply digital filtering, but and in the same time, the current amplitude must be very stable. So the situation can be even more complicated when you have 2 breaks per phase, because the signal will be even more complicated to analyze. With CBA 3000, you can perform the test in both size ground mode using exactly the same wires, the same connections that you are using for the resistance measurement. So with CBA 3000, when the circuit breaker is both sides grounded, you don't have to make any change into the connection. So it makes the life of the operator even easier and still faster. A special attention must be paid for GIS breaker because main contact is inside a metallic enclosure. Have access to what is inside, at least you cannot get it easily. And you would like not to touch anything in the breaker. You don't want to unscrew bars or any part only because you have to make a test on this breaker. The principle that you need to test the timing cannot be the same that you are using for the testing of air insulated breakers. You need to introduce a different method because the resistance of the metallic enclosures in parallel to the main contact is extremely low. Most probably is in the range of a few microns. So it's the same value of the main contact. So during the operation open close, if you just use the measurement of the, let's say, resistance variation, you will not see any variation. So the solution is to introduce Rogowski coils in the path of the current in the main contact. So we have to keep the concept of the current generator. So we need something that injects current, but we have to detect the moment where the current flows only in the contact. Because if you measure the total current out from the DC generator, you will not see any difference because the current that flows into this, let's say, network is basically always the same. But the Rogowski coil gives us the possibility to detect when the current flows into this branch of the network. This is an example. This is the earth disconnector. So you can see that we are not going to unscrew anything. The earth disconnector can remain closed. This is a special clamp because not always you can put standard regular clamps. Maybe you need something like this. And here you place the Rogowski coil. In this way, you can detect the current variations due to only the flow into the main contact. We are a little bit late, so let's go fast, having a quick overview on the CBA 3000. It is provided with configurable hardware. You can have only one of this board, so let's say up to 8 timing inputs, but it can be up to 24. And every input can be programmed by the operator, so the operator can decide the function of each one. The number of commands is also configurable, so you can have only 2 or up to 6. Is very depending on what you need. And all these inputs are programmable. And the same for the analog input. you have up to 8 analog input, but if you count the number of sockets, you have more than 8. The reason is that the operator can decide if the, let's say, channel 1 will be through this banana 4mm socket or a multiple socket. And these are the DC generator. The software give the possibility to perform the test in 3 steps. The first is to choose the right configuration of the instrument, because CBA 3000 is a programmable device. So you have to tell, before to perform the test, what the configuration of the breaker you are going to test. Then you decide a test plan of operations, and in the end you get your results. This is an example of the configuration you have to indicate in the beginning. You have to tell what is the number of breaks per phase, the number of open coils and close, if you want to use micrometers, if the circuit breaker is both sides grounded, yes or no, and so on. Once you perform this setting, then on the screen you can see the suggested wiring, because on the front panel or on the seals, on the panels in general, you don't have a clear, precise indication, because every input is programmable. So you need that something is telling you what is what must be connected and where. But everything is very clearly indicated by pressing the question mark button. There is also the possibility to make a manual configuration, but this is necessary only in very special cases. Then you decide the list of tests, and this test can be saved and executed in a second moment. For example, you can save the test plan and pass to your colleagues the same sequence, so then they don't have to make any setting. They just need to open the file that you are passing. In the end, you press the start button and you have your results displayed in a graphical form, but also in a numerical form, because it's very important to have an algorithm that is making all the measurement and calculation for you. Otherwise, you have to make complex analysis out of this graph. But it's very comfortable to have something already prepared for you. So we are in the end of this webinar. These are my contacts. This is my email, my phone number. You can find me in LinkedIn as well. So if you want to be part of my contacts, feel free, and I will accept it for sure. Okay, so if you have any question, feel free to ask, send me an email. You can even try to call me, keeping in consideration that I am in Italy, so please don't call me when in Italy is night. And I want to remember you that the same webinar will be repeated in Spanish language on the 22nd of November and in French language on the 28th of November. So I thank you all for your attention, and I wish you to see you again in our future webinars.